So again, now we're going to talk about some of the architectural deep dive, talk about how some of the hardware gets used. That was the hardware section. Now we'll talk about the software. How do we put this together? How do we build the box? How do we make this real? Again, Vince Westin and Adnan Sahin here presenting for VMAX. So one of the things that we do with VMAX is we do true non-disruptive upgrades. So in general, it's a second or two of pause, and every director on the box gets loads the new code and implements it at the same time, right? So it's a grab your ankles moment, and the code is.
I had sphincter issues just hearing it.
Yeah, and that's the same thing we've been doing ever since I got here, right? So I've been doing this for 22 years. And we've been doing the same thing on Symmetrics, where you bulk load, you stage the new code everywhere, you make sure everybody's happy, you flip to the new code, and you can go back if there's a problem, obviously, but if everybody agrees, you're up and running and done. So because of that, there is no rolling outage, there is no failover, failback, there is no LUN trespass, right? And to that point, we never drop light on the ports. There is no Fabric logout login. The servers never see the state change notifications or any of that, right? We do this in the background, and the servers are like, yeah, did something change? I didn't see anything, right? Your servers cannot tell that we did a code loop. Right, this is completely invisible.
Keeping in mind the use cases that you mentioned, that people have bought VMAX because of availability and all of that.
Right.
What are you actually seeing in real life scenarios? That you're saying there's a few seconds worth of downtime, but I'm guessing.
No, I'm saying that you take your ATM system and you load this in real time, and nobody notices because there's one I/O that happens to run, part of a second longer than it would have.
But actually, out there with people running it, are they using this, or are they still
every time?
Right.
Oh, yeah, no,
yeah, this is why people buy this box, right? Because I can load code twice a year on every box I've got, and usually I do it off hours, right? But even years ago when we were testing small systems, we'd run them up 50, 75,000 IOs, right? Have the customers walk in, do some tests, hot load code, right? And you're sitting there running the test benchmark, and there's you can barely see that there was that part of a second where nope, it was offline, done, right? There's a slight pause in IO, and you keep right on going. And again, that's one of the reasons people buy this. Another thing that a lot of folks don't realize is if you do that upgrade and then you're looking around your environment, and I've had a couple customers who they do the upgrade and they say, oh my, right? This particular host doesn't know how to deal with the new version because of XYZ. We can do an online downgrade back to that previous revision, same way, right? So not only can you go up, but you can go back to that previous code online.
So what about the dependency situation with your codes? I mean, do you have when you go to a different code on VMAX, if you've got versions of PowerPath, versions of whatever, are there requirements and dependencies outside of that? In
general, unless you're using something like Solutions Enabler that really knows about the array, most of the code couldn't care, right? So if you've got an old version of PowerPath, if you look at the support matrix we have, you can be running PowerPath that's 5, 8, 10 years old. It'll run fine with the new code and the new arrays, even though those arrays weren't even thought of when that code was being built. So we do our best to be very tolerant of up and down on both the host side and the array side. So you can go to newer PowerPath on the host side, you can go to newer code on the array side, mix and match, we don't care. Because asking a customer to be at the same level on everything in their environment, when you may have 1,000 servers connected to an array, is not a reasonable request.
But do you guys do regression testing against all that in your labs?
Yes, we do.
Okay.
We have some amazingly extensive regression tests, which is part of the reason that we spend a little more time trying to release code, right? We don't do this every week. In general, there's a couple of major releases a year, and whether it's maintenance releases or functionality releases, and customers pick one or two of those to pick up, depending on what they want for the features and if any of the things, because we publish the list, right? These are known bugs we found and fixed, right? You can get hot patches for individual problems, or you can just wait till the bundle code has been separately tested as a whole and just load that.
Same process.
Either way.
Hot patches and
yep.
full releases.
Same patch for everything. In fact, most of the hot patches, this is the full IML of a new code load. Most of the hot patches are just an online flick. They don't even do the patching process. So the IML is the initial microcode load. We do hot IMLs on the frame to load new code like that all the time. And again, being able to do the downgrade, right? One of the things your customer has, you've got the list of things you want to do, and one of it is what's your backout plan, right? If it doesn't go the way I wanted, what do I do? And you got to be able to do that. So again, this is part of why customers buy this, and this has been going on for multiple generations. And we've supported online downgrade for quite a while. On the VMAX 3, we actually test it for every code release. It's fully supported on all code releases. So that's kind of a new thing. In terms of the architecture, the redundancy, starts at every level. Active directors or controllers within the bricks. The power is redundant. The battery is redundant. The DAEs have redundant components and redundant power paths, redundant logic paths. We do RAID on the drives. We'll talk about that in a minute. Redundant InfiniBand, redundant management. It's all about failure containment. Right? How do we have the ability to have multiple failures of different things that don't impact the availability of data? Now, obviously, if you start shooting multiples of the same thing, you got a different set of problems. But in general, we want to be able to lose at least one of everything and keep right on running. In terms of the protection, we mirror all the writes, so the writes are always mirrored in cache, and then we destage them later. We do ongoing cache scrubbing continuously. We do ongoing scrubbing of all the data on the drives. So in general, once a day, we will read through every block of data on every drive, read it up into cache, do all the checksums, validate all that, do the checksums of the parity, right? Make sure that everything is healthy and happy. It used to be that in the SCSI drive days, you had seek errors, right? Where you'd write data somewhere and it would seek to the wrong place, put the data in the wrong place on the drive, and you'd go back and read, it's like, yeah, that's not right, right? And so both the data that you intended to write didn't get overwritten, and something else you didn't intend to touch did get overwritten, and you can find those and correct them and deal with all that.
Data drives still do that.
Yeah, so in the flash world, it's much less likely.
Yes.
So we still have the protections in there. We still look for it, but we're not seeing it much at this point. We actually don't see much in the way of flash failures, right? The flash drives give us indications of, hey, I'm getting bad. I'm not having a great time, and so we will proactively copy the data off the drives, and then we'll get around to replacing them and so on.
On the flash stuff, do you have EMC specific firmware inside the controllers, the CPUs on the flash drives you're using? Or are you using off the shelf? I guess would be a little too extreme to say on that front.
So we do not have custom firmware.
Okay.
We do have very specific versions that we use because of our test process with the vendors.
Right.
We used to use custom firmware on some of the drives, and we figured out that means that we wind off on some far branch of the vendor's code and usually leads to bad things. Because over time, they won't keep all the branches up the same. It's impossible for them to do.
Right.
So at one point, we had drives that had the ability to do, RAID parity calculation on the drive. So we'd hand them the new data, and they'd hand us back the deltas, so we could go do something else, right? We got away from that kind of stuff. So there's no more custom firmware on the drives. We do have multiple vendors that supply every size drive that we have.
My secondary question.
And we have all the testing to make sure that we know what the fault levels are like on all the drives and the resilience. And I was going to talk about some of the resilience under write pressure, for example, on flash drives is a totally new thing, right? That wasn't true on the old spinning media, but has a lot of impact on performance on flash.
Good.
So, yeah.
Okay, and scrubbing every 24 hours is a design goal, or?
Yeah.
Okay.
So, I mean, if you have a box that's absolutely hammered, it may take 48 hours to get there.
Right.
But in general, it's just a background task that'll sit and do the scrubbing and read all the data and check it all. And if we get multiple failures off the same drive, we're going to flag it for replacement.
Yeah. Well, I'm dealing with another vendor who shall remain nameless, who's really proud that they managed to scrub everything every 90 days. And the way I do my probability math, that's problematical. And so that you guys managed to get it done every day.
Yes.
I like
We come from a history of having things fail a lot. We don't trust them.
Yeah.
And
those 9 gigabyte drives were just not that reliable.
Yeah, we remember those. But the other thing is that, you look at media changes, right? We're looking toward NVMe DAEs, which are going to be a brand new DAE type, a bunch of new drives. You look at storage class memory, right? You don't know what some of the failure modes are going to be on some of the new things. Having these old protections just stay in the code gives you that much more confidence that when you do the new things, you're not going to introduce problems into the system.
Right. And then we won't buy the new stuff for a year, and you'll find the new failure modes, and you'll build that into the code, and we'll benefit from that. Because I've been a pioneer, and no more arrow S.
Right, the arrows in the back, they hurt, right? You can tell the pioneers. They're the guys pulling the arrows out. So we've got T10 diff. You can do T10 diff on the front if you want from the host to the array. We run it all the way from the front end port down to the drive and back. So we have all the error correction stuff built in addition to all of our other paranoia, right? But that's included in the checksums that we put everywhere.
You guys are students of Andy Grove.
Well, it's one of those, I don't know, Bill Tuber used to be our CFO, right? And in 1999, Tuber had a pile of cash and no debt for EMC. And everybody in the industry said, Bill, you're an absolute idiot. You don't know how to run a company, right? 2 years later, there's the huge crash. We've got $7 billion in cash. We've got no debt. And we can run for the next 18 months, not sell a thing and still be fine. And they're like, Bill, how did you know? He says, there's this thing called a cycle that goes up and it goes down. Same kind of thing with storage, right? We've seen this story before. This is not news to us. We're not doing this for the first time, so we know what some of these things are going to do. And we just don't trust them, right? We're paranoid. Again, belt, suspenders, super glue, tape, all of it. We've got a preemptive event driver. We obviously try and focus on host IOs, right? And so everything that comes in happens dynamically in real time and is managed so that we focus on the host reads and writes. In terms of the RAID layouts, I don't usually talk about this, but you all are an audience that likes to get down a little lower into how we do things, so we thought we'd talk through some of this. When we create a set of flash drives, and we support multiple RAID options, right? We do 3+1, 7+1, 6+2, 14+2. In general, most of our arrays these days are being sold with 7+1 RAID 5. And the reason is that the mean time between replacement on these flash drives is 2.5 million hours. The rebuild times on a 4 terabyte drive is still less than 3 hours right now. I mean, the rebuild times are.
Is it a many to one rebuild or a many to many?
It's a many to one. Well, actually, right now, because when we're rebuilding these drives, they're all copies. They're not being rebuilt. We do a 1-to-1 copy from this drive to a spare. Right. So, and so far we have 100% success that we can copy all the data off before the flash drive actually fails because we're detecting them. Now, that means we're probably replacing some of them a little early, right? Because 100% of them are getting copied off of. We're okay with that.
I have maintenance, you pay for that.
Right. We're okay with being a little early. We'd rather do that than deal with failure. So, people say, well, what are you going to do with the 2 drive failures? It's like, well, once we get the first drive failure, we'll talk about the second. We haven't got the first yet. So, again, with 2.5 million hour mean time between replacements and very short rebuild times, it just doesn't matter. And the system, the drive counts on these things are dropping so fast that who cares? So we can easily exceed 7 nines of designed availability on the drives using 7+1 RAID 5. So that's our go-to way to do it. And as I tell customers, if you're really paranoid and can't live without that data, turn on SRDF. Right, and then you've got the remote mirror on top of it, and you don't care.
Okay, there isn't a 7+2 option?
There's a 14+2, a 6+2, and we can do the RAID 6.
Okay.
Yeah.
Can you just, for those in the
Sorry.
TDAT,
TDAT, right. So the thin data device.
thin data device?
Right. So this is the back end and the back end track. The front end is the TDEV, the thin host device, and the TDAT is where we put the data in the back end. So, yeah.
We're a big company. We have to make up our own words.
Oh, we have so many acronyms. So the interesting thing is we have SRDF, right, which is the Symmetrics remote data facility, right? If any of you have done mainframe always has a facility for everything. So originally, TimeFinder was going to be the Symmetrics remote mirror facility, SMMF. That just rolled right off the tongue. And somebody finally said, we don't have to follow IBM on this stuff. We can do something different and name it something that's more intelligible to humans. But yeah, we got tons of acronyms. We actually have a whole book of acronyms. There's acronyms about the acronyms.
So there's an employee orientation. This is glossary day. We're just going to go over the acronyms.
Thankfully, not that big of a set of acronyms. But yeah, you need to learn it. So what we do, we take the group of flash drives that are set up in a RAID configuration, and we break them into 64 logical chunks. And each of those is a logical data chunk that we're going to put things on. And we lay out data. When you write data, we pick a TDAT, and we put the data in that TDAT. Each one of those is laid out to hold one size of track. Either 8K, 16, 24, 32, whatever the compressed result is, somewhere between 8K and 128K. The reason we do that, a couple reasons, but the primary reason is I don't have to do garbage collection.
Track?
Yeah, so
RAID stripe?
Every bit of data that you write to the array is broken into 128K pieces, which we call a track.
Because you guys have worked with disks for way too long.
Yeah. So we're still living in track pieces.
Okay, but is a track a RAID strip or a RAID stripe?
A track is an individual chunk of data. It's part of a stripe.
It's a strip.
It's one of the strips. So the 128K piece there on the host data can be compressed as small as 8K. And so the back-end TDATs are designed to hold one size of those, specifically so we avoid garbage collection, because this guy's full of all 8K pieces. Well, when I delete one and I write another one and I have to worry about how to make space for a bigger one, they're all 8K. Right? And this guy does all 24s, and this guy does all 128s. And the array can dynamically say, gee, I have more data that's compressing 16 to 1, so I'll delete a TDAT of a size I'm not using and create a new TDAT there that does the 8K 16 to 1 compression.
So, Vince,
So dynamically
how much of this was specifically written for Flash, and how much of this existed before Flash? Because this is a very different layout to the disk model like you used to have. But so did this gradually come in, or was this purely for the Flash?
It was gradual. When we did the VMAX 3, this was 16 splits, and they were all the same size. Right, and then we moved to compression. We dynamically changed these, and we actually did online conversion for customers. Right, delete all these TDATs off, put in 64 new ones of the various compressibility sizes, and now you can turn on compression on the data, and we'll put it wherever it goes. But we specifically built this to make sure that we didn't have to do the garbage collection of small block, large block sharing the same track, and now I got to consolidate the holes to be able to write new things. Because as we looked at how to do compression, we decided we were going to cheat in a couple ways, and that was one. Right, we never want to have to do garbage collection. Right, so much easier to now and then change a TDAT. We usually do that less than once a day on a production frame. Much easier to do that than to consistently do garbage collection on all these little writes that are coming in. Right.
It's an interesting alternative to the more usual log.
Yeah, it's just a different way to do it, but it saves us from ever having to do the log garbage collect stuff. So the host data comes in. Each 28K gets stored in a single TDAT compressed or not. Depending on whether or not it's compressible. And then that's scattered across TDATs across the frame, right? So you can have pieces of every LUN sitting on every RAID group everywhere in the frame, right? One big pool. And that also means we get bandwidth of all those. Yes.
So even though you're not doing chunklet style, to steal somebody else's term, you are wide striping automatically.
Absolutely. Yeah. So, and it's not contiguous. It's not like you have a bunch of contiguous tracks from one LUN. They're scattered everywhere, right, on every individual 128K. The reason we did the 128K is we have our average block size that we're getting in on the front end is north of 40K now, and it's actually moving towards 64K rapidly.
It's amazing how fast that's moving. It was just a couple of years ago. I looked at the data I looked at was about 16K, and now for most of the data I have is for smaller systems, but it's around 32K. So
right. Yeah. So and it keeps going up.
Yeah.
And even the extreme guys will say, well, their average I/O size is closer to 8K, but if the median, I should say, but the mean is actually much larger because they have a bunch of 1 meg and plus larger IOs, and so this allows us to do all of our actual host IO in 128K chunks, so we don't break your large IOs into tiny pieces, so we can keep the bandwidth of the box even while we're doing the compression and such. Yeah, it's been pointed out that I'm going a little slowly. I need to speed this up a little bit.
it's all our fault.
Yeah, it's okay. It's great.
Oh, your fault.
It's all my fault.
It's always my fault. My dad told me that many times.
So data at rest encryption, real simple. Hardware, we compress it on the way down to the drive. We decompress it on the way back. There's one key per drive. You pull the drive out. We shred the key. Right? Not a whole lot to talk about. It's all FIPS validated and done. In terms of the cache management,
Can you get back to the slide before?
yes.
Are you doing that at the entire array level, or can
Yes.
you select to do that on specific?
We do not support the turning it on for part of the array. It's all on.
Okay.
Since it has no performance impact, turn it on, be happy.
And it's
Fantastic.
all on all the time. If you don't want your data encrypted, tough.
Right. Now, it is an option. If you don't buy the FX, you have to pay extra to get it on the F model.
Okay.
Right. So, but most of our customers at this point, the question is, in the next 5 years, will you have to encrypt your data? Since the answer is yes, do it now and be done. Right. So that's a very
If there's no performance impact, there's no reason not to.
right. So we put all the data in and out of cache. We've talked about that a few times. We keep the most recently used data in cache, right? We've got a bunch of cache. We're still getting better than 54% read hits across the world on our frames, which, as you can imagine, makes a big difference on response times and what you can achieve. When you do sequential reads, we create a circular buffer. The read comes in, it goes in the buffer, and it stays for a little while, and it drops right back out. So if you do a bunch of large sequential reads, you won't flood everything else out of the cache. Right, so we've optimized this. Again, we've been doing this for quite a while. We know how to manage these pieces. Writes come in, they're acknowledged to cache. We destage them later. We get two benefits out of this. One is we get to write fold. So if you overwrite a track within the couple of minutes of our normal write fall through time, your writes go to cache and we never have to do the other IO. right? Also, we get to take write coalescing. So if you're doing 8K log writes for your database, we turn those into 128K full stripe writes on the back end, and we don't have to deal with that, right? We're reducing your IOs 16 to 1, makes it much easier on the array. So there's some tricks like that that we do to make it easier on our flash drives. Since you all like to talk about details, we thought we'd go ahead and walk through an actual IO. Obviously, if I do a read and the data's in cache, all right, I come in here, I say, oh yeah, read, grab it out of the memory, put it out. But if I do a read miss, I have to send a signal to the back end that controls the drive and says, hey, fill me up. And so the back end will grab the data off disk, it will load it into memory, and tell me it's there, then I can read it out the front and push it out to the server. Right? And so the data then stays in cache for rereads and such, and to be able to drive things through. On writes, it's a little simpler, right? The write comes in, it gets stored in cache, and it gets mirrored across two different directors. If you have more than one brick, we're going to mirror it across the bricks, right? Make it really simple, and then we can, at a later time, destage that write data. So there's no fixed time in general. We have at least 120 seconds of cache fall through time. So in general, those writes will hang out for a couple of minutes in cache, waiting for other things to happen. We do the same kind of optimization when we're doing remote replication with SRDF, where we take the deltas for 15 or 30 seconds and send them all together. Right? And we don't try and apply each one in order, and because we're not doing that, we get optimizations of write folding. And then, yeah, at some point later, write the data down because it's got to go to disk. Right? So that separates all that. That allows us to do all the writes at cache response times rather than waiting for any media stuff, rather than waiting RAID overhead, whatever else. Right, optimized and done.
You didn't actually mean to imply that SRDF doesn't enforce write order integrity, right?
Actually, I did mean to imply that if you're doing SRDFA, we don't do individual write order integrity. Absolutely. We'll talk about that in a second,
That's
because what we do is we do all or nothing application of all of the changes in a 15 to 30 second window. Well, you can set it as low as 5 if you want.
A, not synchronous.
That's A, not synchronous.
Asynchronous,
exactly.
right? Synchronous, it's all real time.
Yeah.
But we'll talk about RDF in a minute, assuming I don't talk too long. Then we go to do compression, right? I've already talked about how we kind of sort things out with the blocks. So some things are less compressible than others. We run these through our compression engine. The first thing we do is we cheat, right? If you have data in the box that's hot, for the top 20% of your data blocks, the busiest 20%, we don't do compression on those blocks. We leave them sitting uncompressed. Right? Because of that, we avoid the overhead of compression, the read response time, such on 80% of your IOs. Right? Now, if the box fills up to the point where you need the space, we'll compress all of it. Right? But since most arrays run at 60, 70, maybe 80% full, we don't waste our time compressing and uncompressing the busiest 20% of the data. Right? So we absolutely cheat. And then we keep your data together, so the 128K track gets stored whether it's small or large. We compress the pieces and keep them together, but we do it in 432K pieces. So if you do a small 8K read, we can read a 32K chunk, or what will become a 32K chunk off the back, uncompress that, hand it to the host. Right? We don't have to uncompress the whole 128K. So again, this is part of when I said things are a little different. When we went to VMAX 3, we aligned the track size on disk and the track size in cache at the same size. So our old track size, it was 64K in cache and 768K on disk. It was a 12-to-1 ratio. And at that point, you can't really do compression. We know we tried. There are a number of other things you just can't do. Yeah, well, you may remember we tried it for some slow data, and it's like, oh, you want to slow that data down? Just wait. We'll turn on compression. And so because of this, we're able to play some really nice tricks. So we've compressed over 150 petabytes in the first 14 months of availability, and people start slow, so that's really been ramping up lately. So this is an example of a big block workload, because big block tends to push compression harder. I start off at 0.5 millisecond, and as I push the array, we went up to about 0.7. We said, okay, that's about as far as this thing needs to go. It's doing lots of I/O. It's pushing lots of bandwidth. Now, what happens when I turn on compression? And the answer is, well, at low I/O rates, it's doing almost nothing. And as I get out here, yeah, I've got a 15% or so delta as I push it to the wall.
Where you get CPU bound.
Right. You start having real contention of things, but until you start pushing the frame, you get compression for almost nothing. And I have customers who measure sub-millisecond response times. They've turned this on for their production because all they see is double the space.
Yeah.
Right? So because we cheat, because we keep that 20% that's active away from the compression, we don't even add and it's all hardware-based compress, decompress, but it's still 50 microseconds of latency, right? We keep that out of the high-performance IOs. So you're just not having that impact, and this works really well. So we're cheating, but we're making it work.
Okay.